Okay, let's do a quick review of some of the circle information that we've learned up to this point. I'm going to start with number 8. It says find the measure of all the arcs. So I'm just going to go ahead and find the measure of all the arcs all the way around, and then we'll go back and fill in information from the other 7 questions. So vertical angles, this would be 45 degrees right here. I know that I have a diameter right here. So we know that a diameter adds up to 180 degrees. And since this is also a central angle, this angle right here is 15 degrees. So I'm going to take 180 and minus 45 and minus 15. So that gives me 120 degrees. So this angle right here is 120 degrees. You could also use a diameter on this side right here, on the top side, and right here, this diameter, to give you this angle measure inside here. So 180 minus 45, that'll give you that central angle. So 180 minus 45, that's 135 degrees. So remember, if you have central angle, then the arc measure is equal to its central angle. So since its vertex is at the center, that means this arc measure is 135 degrees. This one is 45 degrees, and this is 120 degrees and 45 degrees. All the way around the circle should add up to 360. And remember, there's a difference between arc measure and arc length. Okay, so we'll go back and answer the rest of the questions now. So number 1 says, what's the name of the circle? So remember, we named this circle from the point at the center. So this is circle F, because that is our point at the center. Name a diameter. Well, there's a couple of diameters in that picture. I'm just going to do segment AD. You could have chosen segment EB. Both are diameters. Name a radius. So once again, we could do lots of segments on that one. I think I will just go with segment FC, just so that your endpoint's at the center, and then you have another point on the edge of your circle. Okay, name 2 congruent arcs. All right, so there's lots of things that we could do here that could be congruent. I think I'm going to just go with the easy one right off the bat and say arc AB is congruent to arc DE. Those 2 arcs are congruent. Name a minor arc. So remember, your minor arc just has to be less than 180. So I think I'm going to do arc B to D. I'm allowed to do that. It doesn't have to be a pi segment. I'm going to go B to D. That's 120 degrees. So, or no, that's 120 plus 15. That's 135. So that's less than 180. So I could use that for a minor arc. Major arc, remember, has to be greater than 180. And so you need a starting point, and then another point, and then an ending point, so you know which direction you're moving. So I think I'm going to start with our at D, move in the direction of E, and end at C. So that's a major arc. If I did 360 minus 120, that'd be 240 D. The measurement of it is 240 degrees. Okay, name a semicircle. So remember, a semicircle you can do with 2 letters or 3 letters. So I'm going to say semicircle is the arc, I'm going to say A to D. And then I'm also going to say semicircle ECB. I'm going to do it both ways, ECB. Both of those are semicircles. And then we found the measure of all the arcs previously. Okay, that was a quick review. All right, so now we're just going to learn some more theorems that deal with our circles. So the first one says 2 arcs are congruent arcs if their corresponding chords are congruent and they are arcs of the same circle or congruent circles. So what that means is right here, this circle on the left, this chord right here is the same length as this chord right here. They're marked congruent with that one slash, that one red slash. So then that means in this picture, since they're in the same picture, that means then that arc HG is congruent to arc EF, that one. They're in the same circle, those arcs are congruent. Over here, I have two different circles, and I have the chords marked congruent, so I know that LM is congruent to NO. But in order for arc LM to be congruent to arc NO, those two chords have to be in the same circle or they have to be in congruent circles. And I know that these two circles are congruent because the radius in each of those circles is marked congruent. It's got one red slash. That means they're the same length. So those two are congruent circles. So I can say that arc LM is congruent to arc NO. That's true because the circles are congruent. Okay, this third scenario down here, when I built this, I actually measured it so that this arc right here is the same length as this arc right here. So let's put some letters in. I'll call this A, B, C, and D. So what we want to know is, I know the two chords are congruent. Is arc AB congruent to arc CD? Well, the circles are definitely not the same. And so the theorem says that it's got to be in the same circle or congruent circles in order for those two arcs to be the same. So we're going to say that's a no-go. I can show you that. I'll drag that over so you can see how that looks. Just a minute. So I'm just going to drag this circle and line up those chords. And you can obviously see that those two arcs are not the same. So once again, in order for that to be true, the chords have to be in the same circle or in congruent circles in order for the arcs to be congruent. Okay, in this slide right here, it says in each problem tell whether arc AB is congruent to arc CD or the measure of arc AB is congruent to the measure of arc CD. So those are two different things. Remember, the arc measure is talking about what its measurement is pertaining to the central angle associated with that arc. Just talking about arc AB congruent to arc CD, that's when we're talking about the physical, what does that arc look like? So question number one is a really good one to point out the differences. So this is a central angle right here from AE to B, this central angle. Just for sake of giving it a measurement, I'm going to say this is 70 degrees. All right, if I wanted to find the arc measure of CD, so the measure of arc CD, remember that's the same thing as its central angle measure, so that's going to be 70 degrees. Okay, I'm going to find the arc measure of AB. Well, once again, that's the same thing. It's the measurement of its central angle that's associated with that arc, so it's got to be 70 degrees. So in this particular picture, the arc measures are the same. They are 70 degrees. The measure of arc AB does equal the measure of arc CD. But are the arcs congruent? No, they're not. You can tell that arc CD, if I were to get out some kind of measuring tool, is definitely shorter than arc AB. So to answer our question for part A, is AB, the arc AB, congruent to arc CD? That's going to be a no. They're not congruent. Part B, yes, the measure of arc AB does equal the measure of arc CD. They have the same central angle measure. I gave it 70 degrees, but you could have picked any number. So yeah, they're the same. Okay, over here on the right, number 2. So it looks like to me that we have two congruent circles. That's important. How do I know they're congruent? Because each of them has one of their radius marked with one slash. So that means those two segments are equal, which means those two circles are equal. So to answer the question then, for part A, is arc AB congruent to arc CD? Well, they've got the same central angle, so that would mean then that they have the same radius length. So yes, these two arcs would be the same measure. Oh, excuse me, they would just be congruent. We're doing arc measure here in just a second. So arc measure would be looking at our central angle measurements, and since the circles are equal, I guess that doesn't really matter if we're doing arc measure. All we care about for arc measure are the central angles equal, and yes, the central angles are equal, so the measure of arc AB does equal the measure of arc CD. That is true, that's yes. Okay, down here on the bottom, we want to know if AB is congruent to CD. So remember on our last slide, the last theorem said that if this chord was congruent to this chord, then arc AB and arc CD would be congruent if they're in the same circle or congruent circles. So these are not in the same circle, and those do not look like congruent circles to me. So for part A, arc AB is not congruent to arc CD. And then what about their arc measures? Well, I don't have the central angle figured out here on that one, so I don't have that one drawn. So the measure of arc AB to the measure of arc CD, we're going to leave that one alone for just a minute since we didn't put in the central angle to figure out that measurement. Okay, let's move on. So here's another one that says, another theorem that says, if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So you have to pay attention to notation here. This right here does not have a center circle drawn. So if you don't see that center point drawn in there, then you cannot assume that that's a diameter. So that's kind of important in these next couple of theorems. So right now I cannot assume that's a diameter. But if I know that it is both perpendicular and a bisector, then it would have to go through the center, and then it would be a diameter. That's what the theorem is telling us. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Okay, so why does it have to be both? So let me show you a scenario where here's a segment, and here's a line that's perpendicular. Okay, but that obviously didn't cut that into two equal parts, so that segment's not a diameter. Okay, what about if I did it so that they would be equal? So what if I took my segment here and I found the centers right here, but look what happens if I draw it at a diagonal. These two pieces are the same. I could measure those out, but once again, that's not a diameter. Both characteristics have to happen. It has to be a perpendicular bisector in order for it to be a diameter. Okay, question number 1 says find the measure of each arc. So I'm going to come down here and look. I cannot make the assumption that this is a diameter yet because, number 1, I don't see this little center point, so I can't assume it's a diameter, but maybe I could use the theorem we just learned to decide if it truly is a diameter. So what has to happen? This segment right here that we're trying to decide if it's a diameter has to be a perpendicular bisector of the other chord. Well, here we go. We've got that it's marked congruent and we've got perpendicular. So yes, it's a perpendicular bisector. So that means, yes, indeed, that is a diameter. You could put the center in if you wanted. So this arc measurement right here would have to be 60 degrees. It's going to be the same as the other side since it's a perpendicular bisector. And then the other two would be 120 degrees. Since we know it's a diameter, there's a semicircle on each side. Okay, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Okay, so this is going the other direction now. So I am telling you that it's a diameter and it's perpendicular to a chord. So if it's perpendicular, then we know that this part of the chord is congruent to this, and then this part of the arc is congruent to that part of the arc. That's what it's telling you. So down here it says find RS. So notice in our notation, I see the center line or center dot. So I know this is a circle and it's marked perpendicular. So that means this part of the chord and this part of the chord are equal, and those two arcs are equal. Well, we're trying to figure out what x is, so I guess we'll just put them equal to each other. X plus 4 equals 3x minus 12. Solve that for x. You get 16 equals 2x, so x equals 8. We want to know what RS is. So if I plug the 8 back in, 8 plus 4 is 12. Whoops. So we've got 8 plus 4, and so we've got 12 plus 12, so RS is 24 units. 12 plus 12 is 24. Okay, another theorem. So this one says, in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. So this picture here at the right shows that we've got two chords. Here's AB and here's DC. And we want to know if they're congruent. Well, they're only going to be congruent if they're equidistant from the center. So this piece right here has to be the same as that piece. So if we mark that, I guess I didn't mark that. So if we mark those two congruent, then that's what it's saying. Those two are going to be equal. So in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. So you also have to be, it has to be perpendicular distance. It's not just any distance. It's the perpendicular distance makes them equal, because the perpendicular distance is the shortest distance from one point to another. So that's the distance we're looking for, those perpendicular distance. Okay, so this one down here says find the measure of arc AB. All right, well, I'm looking at it and I see that I have it marked congruent from the center and it's perpendicular. So that tells me then that chord AB is the same thing as chord DC. Well, from a previous theorem, we learned that if the chords are the same length and they're in the same circle, then the arcs associated with those chords are congruent. So arc AB is congruent to arc DC. Well, I know that all the way around and outside of the circle is 360 degrees. So I've got 100 and I've got 40 degrees marked off on each of those. So 360 minus 140 would give me 220, and I'm going to split that evenly. So each of these would be 110 degrees. Arc measures would be 110 degrees. So find the measure of arc AB. So the measure of arc AB is 110 degrees. Okay, here's another one. It says find the measure of each indicated arc in the diagram. So we just need to make sure that we're following our theorems and we can assume that things are equal. So right here's the center of our circle. We have a diameter that goes through that center and it's perpendicular to another chord. So our theorem says then if it's a diameter and it's perpendicular, this chord is bisected and these two arcs are congruent because it's bisected also, the main arc's bisected. So we're trying to find the arc AB. So we're trying to find the measure of arc AB. Well, I guess we better figure out what x is. It looks like to me 9x would be equal to 80 minus x. So 9x equals 80 minus x. So 10x equals 80. So x equals 8. So that means 9 times 8 is 72. So the measure of arc AB is 72 degrees. So this is 72 degrees. And this side right here is 72 degrees. Well, this is a diameter. So then this must be 108 over here and 108 here. Okay, find the measure of arc AC. Well, we'll just add 72 plus 72, and that'll be 144 degrees. The measure of arc C to D is 108 degrees. We talked about that one. And then the measure of arc ADC. So remember, you have to go in the direction that it says. So I'm starting here at A, going to D, and I'm ending at C. So I add 108 and 108. That would be 240 16 degrees. Okay, last one. If a chord is 3 inches from the center of a circle and is 8 inches long, find the diameter of the circle. Okay, so what I would do is I kind of draw these all the same way. You're going to have a bunch of questions in your homework that kind of deal with this scenario. I just draw them all the same way. First thing I do is just draw a T. So I put in my diameter, and then I just put in a random chord right there. And then because of our circle theorem that we learned earlier that says that if this is a diameter, and I'm going to draw it, when I draw this chord, that's why I did a T, I'm going to draw it so that it's perpendicular. Then I know that it bisects. That's equal to that. That's kind of important. Then the last thing I do is I just put in a radius. And now, if you can see, you've created a right triangle there, and now everything that we've learned with right triangle trig, we can use in this circle. So let's go ahead and see what it says. If a chord is 3 inches from the center, okay, so now remember, this was the original chord I drew right here. So it's 3 inches from the center. So from here to there is 3 inches. So if a chord is 3 inches from the center of a circle and is 8 inches long, so that means the whole chord is 8 inches long. So that must mean then, since it's bisected, this side is 4. Then find the diameter of the circle. Okay, well, guess what? I'm not going to use the diameter that I drew in because it's not part of my right triangle. I want to use my right triangle. This is actually a 3, 4, 5, right? It's a Pythagorean triple. This radius right here is 5. Well, if you know a radius, you know the diameter. If the radius is 5, then the diameter is 10. So whatever our units are, our diameter is 10. Okay. I think that's it for this section.